Good afternoon to everyone. Today I'll be discussing the design of purlins and rafters for timber members. Learning objectives at the end of the chapter should be able to identify the purlin and rafter in a wooden roof system, determine the types of loads that act on the purlin and rafter, analyze the shear and flexural stresses acting on the purlin and rafter, and check the adequacy of cross-section from shear and bending stresses. So for our introduction, the image on the left side shows a simple roof system wherein the longitudinal member here is called the purlins. Meanwhile, the inclined beam that's on the transverse direction is called the rafters. Okay. So the image on the right side shows a simple roof system. As you can see, apparently it only has rafters so far. Okay. So for the definition of the purlins and rafters, so a rafter is a slope beam that supports the entire roof of a building. It also carries roof live loads and wind loads. Purlins, on the other hand, is a horizontal structural element found in a roof whose purpose is to resist wind loads and weight of the roof. So purlins can be commonly made up of timber material or a C-shaped steel section. So for the geometry of purlins and rafters, so the pitch, it is the ratio of the height of the truss, the length of the bottom chord. Roof pitch angle is an angle made by the rafter with respect to the horizontal. Spacing of purlins is denoted by the variable s. And the last geometry for purlins and rafters is the base spacing of truss. Technically, this is called the spacing of the rafters. Okay. So for the loads resisted by the purlins and rafters, so for a purlin rafter wooden roof system, we can see that there are three common types of loads that act on it. So first one is the roof dead load. So and roof live load. So these two, roof dead load and roof live loads, are gravity loads. Thus, they are projected. The load is projected towards the ground. Okay. So for the roof dead load, so the load is projected to the inclined length of the rafter, while the roof live load, on the other hand, is projected towards the horizontal length of the um, rafter. Okay. Meanwhile, wind loads is projected on the vertical height of the inclined rafter. So that is the difference between the three common types of loads resisted by purlins and rafters. Okay. So for the loads resisted by purlins, so for the roof dead load, so as you can see here, it is a gravity load that is projected on the inclined length of the uh, rafter. Okay. So in order to determine the load, so since the um, gravity load does not apply on the um, normal axis of the member, or sorry, the purlin, since the purlin is rotated due to the roof pitch angle, so we need to determine the components of the loads of the roof dead load into we need to determine the components perpendicular and parallel um, to the direction of the purlin. Okay, sorry, parallel and perpendicular to the cross section of the purlin. So for um, For the roof dead load, so as you can see here, um, considering the since this is an since the normally the loads are given in um, pascals, so we need to convert it first into normal line load, such that we need to determine the magnitude wherein it is the load is applied on one of one strip of purlin. Okay, so for that we need to determine the P sub D, which is the roof dead load in pressure, multiplied by the spacing of purlins. So multiplying um, the roof dead load in pressure to the spacing of the purlin, we can get the um, equivalent line load of the roof dead load. So as you can see here, um, the area load is converted into a line load. So these supports are the rafters. So since a roof system, there are many rafters, so that is called the base spacing. So the purlin is simulated as simply supported. Okay. So in order to determine the normal and tangential component, so we can use trigonometric functions to determine the corresponding values for the um, normal component of dead load and the tangential component of the dead load. For the roof live load, so it is different from the roof dead load, since the roof dead load acts on the inclined length of the rafter, while the roof live load acts on the horizontal projection of the inclined length. So in order to be able to relate those two, the roof dead load and the roof live load, we need to convert the project. We need to change the projection of the application of load from a horizontal projection to the inclined length. Okay, so in order to do that, we need to multiply the load by the cosine theta, where theta is the roof pitch angle. So after multiplying cosine theta to the load, so the projection will change from horizontal to the inclined length. So in this case, so W sub L will be equal to P sub L, where P sub L is the roof live load and pressure, multiplied by the spacing of the purlins, times cosine theta, where theta is the roof pitch angle. So this will be the same for the roof dead load, wherein the area load will become a line load acting on the span of the purlin. Okay. So for the support of the purlin will be the length of um, the span of the purlin will depend on the base spacing of the rafters. Okay. So after getting the equivalent line load, so we can get the components for the normal and the tangential roof live load um, by trigonometric functions. Last is the wind load. So initially the wind load is projected to the acts on the vertical projection of the inclined length of the rafter. So in order to change the projection of the wind load from the vertical to the inclined length, so we will need to multiply the pressure, or sorry, the wind load in kilonewtons per meter squared, or psi. So we need to multiply it by the factor of 2 sine theta over 1 plus sine squared theta, where theta is the roof pitch angle. So this will make the projection of the load from normal, so rather vertical to normal wind load. So it is different in the case from the roof live load, where the projection is no, sorry, they have the same projection to the inclined member. However, the application load for the wind load becomes normal to the surface of the purlin, rather than pointing downwards towards the ground, since the roof live loads and dead loads are gravity loads, so they act towards the ground. Okay, so in this case, um, for the wind load, we're only considering the normal wind load, or rather normal to the surface of the purlin, since the application of load for the roof will be the forces acting on the perpendicular to the roof surface. Okay, so the length of the span for the considered for the purlin will be the base spacing for the rafters. Okay, so for the normal wind load will be equal to Pn multiplied by S, where the P sub n is the normal component of wind load and pressure, multiplied by the spacing of the purlins. Okay, so for wind load, so kindly remember that um, that we only consider the um, loads normal to the surface of the roof. Okay, so for the after getting the components for the normal and tangential components for the different kinds of loads acting on the purlins, so the total distributed load in the normal direction will be equal to the sum of the um, norm normal component of the roof dead load plus the normal component of the roof live load plus the normal component of the wind load. So for the total distributed load for the tangential direction, it will be the sum of the tangential uh, load of the roof dead load and load tangential component of the roof live load. For the maximum shear and bending moment of the purlin, so for the shear, B sub n max, so this is the maximum shear in the normal direction, will be equal to the total load for the normal direction multiplied by the length of the span over 2. So this is the same for getting the shear force on the tangential direction. For the bending moment, we have mn max will be equal to wl squared over 8, wnl squared over 8. So this is the getting the maximum moment for a simple beam with uniformly distributed load is wl squared over 8. So getting the component, so the normal bending moment rather, is the you will need to use um, the total loads acting on the normal direction of the purlin. So that is true also for the tangential bending moment. Okay. For W sub n, W sub t, use the higher governing load combination for each direction. Okay. So for the maximum shear stresses and flexural stress on purlins, so for the shear stresses, so shear stress on the normal direction, 1.5 shear force on the normal direction or the area of the purlin. So this holds true to the tangential um, shear stress. Okay, you will so you will need to use the maximum shear force for the tangential direction. So for the flexural stresses for along the normal direction, so that will be equal to the maximum normal bending moment over S sub xx. For the maximum flexural stresses on the tangential direction, FB sub t will be equal to the maximum bending moment in the tangential direction over SYY. So for the total shear stresses and bending stresses in Purlins, so for the shear stresses, uh, you will need to determine the square root of the square for the shear stress in the normal direction squared plus the shear stress in the tangential direction squared. Meanwhile, for the bending moment, so the max total bending stress will be equal to the sum of the normal and tangential bending stress. The total deflection in Purlins. So the total deflection will be equal to the square root of the deflection along the normal direction squared plus the deflection on the tangential direction squared. Okay. So the formula, the 5W L to the fourth over 384 AI. So this holds true um, for uniformly distributed load. So that will be the maximum deflection. Okay, for using that case scenario. So next we will discuss the load resisted by the rafters. So um, I hope you learn the different loads resisted by the purlins. So see you on the next lecture.